Hi guys, and welcome to a new lesson where we are going to review the Python data types on the crash course section of the core Python basics. So Python supports many powerful data types. Superficially, these look like their counterparts in other programming languages, but in Python they often come with superpowers. Everything in Python is an object and therefore has methods. This means we can perform a host of operations on any variable. The built-in dir and help functions that we talked about in the last lesson. This function will reveal all about the data types. So in this section we are going to look at the standard data types and their most important operations. And I will also encourage you to go to the Python reference manual, which provides you all of the details that you need. I can show you Python is a very well documented language, so I highly advise you to explore these possibilities. And you need to be aware of some underlying concepts in Python. First, Python variables are just names. You create variable names by assigning them to objects that are instances of types. Variables do not, of themselves, have a type. It is the object to which they are bound that has a type. The name is just a label, and as such it can be reassigned to a completely different object. Assignment is performed using the equal sign. So assigning a value to a variable looks like the example here: a variable equal to a value. So it could be, for example, host equal to dog, for example. And this code binds the value a value to the variable name a variable. And if the name does not already exist, the interpreter adds the name to the appropriate namespace. The distinction between a variable and its underlying value, which is an object, is thus crucial in Python. You can test variables for equality using a double equal sign and object identity. That is, if two names refer to the same object, is compared using the is operator, and we can have a look at it in the interpreter. If you have installed the same ID as me, PyChar, you have a Python console in there. So if you have trouble, get it to work in Windows. But sometimes I've experienced that the code execution is a little bit poorer inside here than from here. So that was the tip of the day. So let's just play around with assigning values. Type in an integer. The first two are strings. So now we assign another variable with an int, which has the value of 6. So both these instances have value of 6. So now we're going to test equality of value. We're checking if the A string and another string has equality of value. They have. Now we're checking the test. We are testing the object identity, if they are the same. They are not, because they are two different instances. And now we're checking if they have the same value. They have, because they both have the same value of 6. And we are also checking if they have the same object identity. They are, because it's pointing to int alias is pointing to an int, so they have this same object identity. So Python groups types according to how you can use them. For example, all types are either categorized as mutable or immutable. If a type is immutable, it means that you can't change an object of that type once it's created. We can create a new data item and assign it to the same variable, but we cannot change the original immutable value. Python also supports several collection types, sometimes referred to as sequences. Strictly speaking, collections are a subset of sequences. This distinction will be made clearer later in another lesson. Sequences share a common set of operations, although not all sequences support all of the operations. Some Python data types are callable. That means you can use the type name like a function to produce a new instance of the type. If no value is given, a default value is returned. We will see examples of this behavior in the following description of the individual data types. So now that we understand the basics of working with Python data types, it's time to look at the different data types, including the numeric, Boolean, and the none type, as well as the various collection types. So numeric types are integer and float. For example, Python supports several numeric types, including the most basic forms, integer and floating points. Python integers are unusual in that they are theoretically of infinite size. In practice, integers are limited by the size of your computer's memory. Integers support all the usual numeric operations, such as addition, subtraction, multiplication, and so on. You perform arithmetic operations using traditional infix notation. For example, to add two integers, we simply type them into the interpreter, or we can type it like this and print out the results. Excuse me. So literal integer values are by default expressed in decimal, and we can use other bases by prefixing the number with a 0 and the basis initial. Thus binary is represented as 0b and n. Prefixing the number with a 0 and the base initial. Thus binary is represented as this is how binary is represented. This is octal 0 O and this is hexadecimal. The type of an integer is int, and we can use it to create integers from floating point numbers or numeric string representations, such as 1, 2, 3 in quotes. So let's create an integer from a floating point. Let's create an integer from the string 1, 2, 3. Int can also convert from non-decimal bases, covering any base up to 36, not just the usual binary, octal, and hexadecimal, using a second optional parameter. To convert a hexadecimal base 16 string representation into an integer, I'll show you an example of that. Python floating point numbers are of type float, and like int, we can use float to convert string representation like 12.34 in quotes to float, and we can also use it to convert an integer number to a float value. Unlike integers, float cannot handle strings for different bases. The float type also supports the normal arithmetic operations as well as several rounding operations. And Python floats are based on the Institute of Electrical and Electronic Engineering, also shortened to IEEE standards, and have the same ranges as the underlying computer architecture. They also suffer the same levels of imprecision that make comparing float values a risky operation. Python provides modules for handling fixed precision decimal numbers like decimal, the decimal module, and the rational fractions, the fractions module, to help alleviate this issue. Python also natively supports a complex or imaginary number type called complex. These are typically used for fairly special processes, so I will not be covering it in this course. And next we have the Boolean type. Python supports a Boolean type bool with literal values true and false. The default value of a bool is false. That is, bool in parentheses yields false. Python also supports the concept of truth-like values for other types. For example, integers are considered false if their value is 0. Anything else is considered true. The same applies to float values, where 0.0 is false and anything else is true. We can convert Boolean values to integers using int function, in which case false is represented as 0 and true as 1. The Boolean type has most of the Boolean algebra operations we'd expect, including and, or, and not, but surprisingly not XOR. And Booleans are implemented as subclasses of integer, and so also support a bunch of operations that we might not expect, such as exponentiation. We can type things like and get the result of 1, and we should basically just pretend these features don't exist and treat them as an implementation detail. Otherwise, our code will be very, very confusing. In addition to the Boolean type, Python also supports bitwise Boolean operations on integers. That is to say that Python treats each corresponding pair of bits within two integers as Boolean values in their own right and applies the corresponding operation to each pair of bits. These operations include bitwise AND, like this, or this operation, NOT this operation, XOR this operation, as well as bit shift operators for moving bit patterns left or right. These examples here. And we'll look more closely at these bitwise operations later in another lesson. And then we have something called the none type. The none type represents a null object. There is only one none object in the Python environment, and all references to none use the same single instance. This means that equality tests with none are usually replaced by an identity test, like so. A variable is none, rather than a variable is equal to none. None is the default return value of a Python function. It is also often used as a place marker or flag for default parameters in functions. None is also callable and so cannot be used as a conversion function to convert other types to none. None is considered to have a Boolean value of false. And then we have the different collection types. And also mention, Python has several types representing different kinds of collections or sequences. These are strings, bytes, tuples, lists, dictionaries, and sets. And we will see the similarities. And so, as already mentioned, Python has several types representing different kinds of collections or sequences. These are strings, bytes, tuples, lists, dictionaries, and sets. We will see the similarities and differences in each as they are discussed in the next lessons, or each section of this lesson. A standard library module called collections provides several other more specialized collection types. We will see occasional references to these in the sections. And in many of the following, what I'm going to talk about, the talks, we will see references to operations accepting a collection type. Usually this includes what Python calls iterables, which are objects that conform to Python's iteration protocol. In simple terms, iterables are objects that we can use in loop constructs. In most cases, we will not need to worry about them, but they are described in the Python documentation. So I would recommend, if you're interested in reading the technical details, you can just look at Python documentation regarding iterators. So several common features apply to all collections, and rather than bore you by repeating them for each type, I'm going to cover it here. So we can get the length of any collection in Python by using the built-in len function. So it takes a collection object argument and returns the number of elements. We can access the individual elements of a collection using indexing. And we do this by providing an index number or a valid key value for dictionaries inside square brackets. Collection indices start at 0. We can also index backward from the end by using the negative indices, so that the last item in the collection will have an index of -1. I'll show you in a minute. Whereas indexing is used to access just one particular element of a collection, we can use slicing to access multiple items in the collection. Slicing consists of a start index and an end index and a step size, and the numbers are separated by columns. Slicing is not valid for dictionaries or sets. The step size argument enables us to, for example, select every other element. All values are optional, and the defaults are the start of the collection and the last item in the collection, and a step size of 1. The slice return consists of all selected elements from start to end minus 1. So I'm going to give you a few examples of slicing applied to a string entered at the Python interpreter. This will give us a sliced version of the string starting from the 4th element, which is 3. This will give the section of the string where it starts from the 1st element up till and including the 3rd element. Starting from the 4th element and up till and including the 7th. Almost the same as the first one, but just the step is taking every 2nd element. This gives us the from end to finish and steps. 3 steps. Take the 3rd element of each step. We can sort most collections by using the sorted function. The return value is a sorted list containing the original collection elements. Optional arguments to sorted provide flexibility in how the elements are sorted and in what order. In general, empty collections are treated as false in Boolean expressions and true otherwise. 2 functions, any and all, refine the concept to allow more precise tests. The any function takes a collection as an argument and it returns true if any member of the collection is true. The all function takes a collection as an argument and returns true if and only if all the members are true. And now I'm going to talk about strings. Python strings are essentially collections of Unicode characters. The implications of using Unicode are discussed in section 5. The default encoding is UTF-8 for strings. If we are working in English, most things will work as we expect. And once we start to use non-English characters, things get more interesting and complex. For now, we will be working in English and sticking with UTF-8. Python requires that literal strings be enclosed within quotation marks. And Python is extremely flexible in this regard and accepts single quotes. I'll show you. For example, if you wanted to, let's say, name Joe, it takes both in single quotes and in double quotes. It's the same. And even triple quotes. To delimit a string. Obviously, the start and end quotes must be of the same type, but any other quote can be contained inside the string. This is most useful for apostrophes and similar grammatical cases. Like let's just give an example of sentence. So if you wanted to make a apostrophe here, we use double quotes on the string, but on the apostrophe we use the single quote. So triple quotes of either type can span multiple lines. I'll just give you some few examples. The interpreter recognizes that more is coming. It hasn't executed the command because it's expecting more with the 3 dots. So a literal string at the start of a module, class, or function that is not assigned to a variable is treated as documentation and displayed as part of the built-in help output for that object. So if we put normally most developers use 3 quotes for instructions and information on the module or the code they are writing, and by calling the help function on that module, it will give us the documentation strings. Special characters such as tabs or new lines must be prefixed or quoted with a backslash character, and literal backslashes must be quoted so they look like double backslashes. We can avoid this by preceding the entire string with the letter R for raw to indicate that special character processing should not be done. Non-printable characters can be included in a string using a backslash followed by their hex code. For example, the escape character is an example. Note that there is no leading 0 as it is used for hexadecimal integer literals. Strings are immutable in that you cannot directly modify or add to a string once it is formed. We can, however, create a new string based on an existing one, and that is how many of the Python string operations work. Python supports a wide range of operations on strings, and these are mostly implemented as methods of string class. So I would recommend you to always use the documentation. Here, what I did, like if you wanted to find the methods for a string, methods on string, you can go to the documentation and find it here. String methods. These are all the methods that you can use for string. There is a lots of fun you can have with strings. So check out the documentations for each type of collections. And empty strings are treated as false in Boolean expressions. All other strings are treated as true. And the next collection type I'd like to talk about is bytes and byte arrays. And Python supports 2 byte-oriented data types. And a byte is an 8-bit value equivalent to an integer from 0 to 255 and represents the raw bit pattern stored by the computer or transmitted over a network. They are very similar to strings in use and support many of the same methods. The type names are spelled as byte and byte array, respectively. Literal byte strings are represented in quotes preceded by the letter B. Byte strings are immutable. Byte arrays are similar, but they are mutable. In practice, we will rarely use byte strings or byte arrays unless handling binary data from a file or network. One issue that can catch us by surprise is that if we access an individual element using indexing, the return value is an integer. This means that comparing a single character byte string with an index string value results in a false response. The response is false, which is different from what would happen using strings in the same way. So let me show you an example. Checking the first element of S, if it's equal to the whole C sequence. Now we're checking the first element of S and first element of C. That's true. So as we can see, the key is to use indexing on both sides of comparison. And we can use the struct module to convert binary data from the bytes representation to normal Python types. Of course, to use this, we will still have to know what types the byte patterns represent in the first place. Empty byte strings are treated as false in Boolean expressions. All other byte strings are treated as true. And the next collection type is tuples. And tuples are collections of arbitrary objects. The fact that they are collected together suggests that there is probably a logical connection between them, but the language puts no restriction on the objects contained. Tuples are often described as being the Python equivalent to records or structs in other languages. Literal tuples consists of a series of values or variables separated by commas, often to prevent syntax ambiguity. The tuple as a whole will be contained in parentheses, but this is not a requirement of the tuple itself. Tuples are also immutable, so we cannot modify or extend the tuple once it is created. We can create a new tuple based on an existing one in the same way we did for strings. And we can create a new empty tuple using the tuple type function. By using this function, we can create a tuple. We can use a tuple as a key in a dictionary because they are immutable. One feature of Python tuple that is very useful is known as unpacking. This enables us to extract the value of a tuple into discrete variables. We must often see this when a function returns a tuple of values and we want to store the individual values in separate variables. So I'm going to show you an example with the divmod function, which returns the quotient of and remainder of an integer division as a tuple. This is the quotient, and this is the remainder. So notice how Q and R can be treated as new single valued variables. A named tuple class in the collections module allows elements to be indexed by name rather than position. And this combines some of the advantages of a dictionary with the compactness and immutability of a tuple. Empty tuples are treated as false in Boolean expressions. All other tuples are treated as true. And the next section collection type I'm going to talk about is lists. And lists in Python are highly flexible and powerful data structures. They can be used to mimic the behavior of many classic data structures and to form the basis of others in the form of custom classes. They are dynamic and, like tuples, can hold any kind of object, but unlike tuples, they are mutable, so we can modify their contents. We can also use tuple-style unpacking to assign list items to discrete variables. A literal list is expressed as a comma-separated sequence of objects enclosed in square brackets. We can create an empty list either by specifying a pair of empty square brackets or by using the default value of the list type function. Lists come with several methods for adding and removing members, and they also support some arithmetic style operations for concatenating and copying lists in a similar fashion to strings. We can initialize a list directly by using lists of values, or we can build them programmatically using list comprehensions. And we can try an example, which is a single line for loop inside list brackets. In many other languages we use I, but here I'm just using, you can use whatever you want. And empty lists are treated as false in Boolean expressions. All other lists are treated as true. And I would highly recommend you take a look at the Python documentation for the list operations that are available. And the example that we just showed here is it's an operation that builds a list of the even squares from 1 to 10. And the next collection type is dictionaries that I want to talk about. Dictionaries are super powerful data structures that that beginners frequently overlook. They offer solutions to lots of common programming problems. A dictionary is used like a list, but its elements are accessed by using a key value mechanism rather than a numeric index. The elements of a Python dictionary are thus a non-order sequence of key value pairs. The key can be any immutable value, including a tuple. Keys must be unique. The value can be any kind of Python object, including another dictionary, a list, or anything else that Python recognizes as an object. Dictionaries are highly optimized, so lookup times are very fast. In fact, Python makes extensive use of dictionaries internally to implement namespaces and classes, among other things. Dictionaries also provide a solution anywhere that dynamically named values need to be stored and accessed. Dictionaries are also efficient when the keys are not sequential, because Python uses a hashing algorithm to map the keys into a sparse array structure. And what it means that is Python dictionaries are fast and they use memory efficiently. Dictionary literals are composed of comma-separated key value pairs. The keys and their values are separated by colons, and the whole is contained in a pair of curly braces. I'll show you an example of a dictionary. And we access the stored values by indexing the dictionary using the key rather than a numeric index. If the preceding example was stored in a variable called d, let's just put that in a variable called d. We could access the A key and the true values like this. We can create an empty dictionary by using an empty pair of braces or by using the default value of the dict type function. Dictionaries come with some extra operations for extracting list of keys and values and handling default values. And I would recommend that you also check this on the Python documentation page. Dictionaries are, by the nature of the implementation, unsorted. Indeed, the order may change when new data is inserted. The collections module contains an ordered dict class that maintains the order of insertion, should that be required. The sorted function returns a sorted list of keys if the keys are comparable. And if the keys are incompatible, as in the preceding example, sorted raises a type error. The collections module also provides a default dict class that enables us to specify a default value that is returned anytime a non-existent key is used. In addition to returning the default value, it also creates a new element for the given key with the default value. This is similar to the setDefault method. This can be a mixed blessing because it can result in bogus entries for badly spelled keys. And empty dictionaries are treated as false in Boolean expressions. All other dictionaries are treated as true. So the next section I'd like to talk about is sets. Sets embody a mathematical concept that is frequently used in programming where a unique group of elements is required. In Python, sets are a lot like dictionaries with keys but no corresponding values. Sets have the Python type set. The same basic rules apply as for dictionary keys, in that set values must be immutable and unique. The default value from set is the empty set, and this is the only way to express an empty set because curly brackets is already used for an empty dictionary. So using this function for creating a set, and this function accepts any kind of collection as its argument and converts it to a set. Dictionary values will be lost. There is another type of set in Python called frozen set that is immutable and is basically a read-only set. Its constructor works like set, but it supports only a subset of the operations. You can use frozen set as an element of a regular set because frozen set is immutable. Set literals are expressed with curly braces surrounding elements separated by commas. So you can create a set like and sets do not support indexing or slicing, and like dictionaries they do not have any inherent order. The sorted function returns an ordered list of values. Sets have a bunch of math style set operations that are distinct from other collections. So please check out the documentation for set methods on the Python documentation. And empty sets are treated as false in Boolean expressions. All other sets are treated as true. So this was the lesson about the various data types. And remember, we are still on the crash course, so I'm not covering all the basics. So I expect that you do some research on your own because that's part of being a programmer. So in the next section, we will, in the next lesson, we will use the data types in code as we explore the different control structures that Python offers, how to structure a program. So see you in the next lesson.